Absolute 0. 4 minus 196 degrees Celsius. Absolute 0, 0 K equals minus 273 degrees Celsius. 4b. Increased pressure. Particles of gas move faster or have more K momentum velocity. Ne2 from. More frequent collisions of particles with walls. Particles collide with walls with a larger force or larger impulse. Greater change in momentum of particles causes greater force on walls. Pressure equals force area. 4c. Pressure equals 60 kilopascals or 6.0104 pascals. P1V1 equals P2V2 or P2 equals P1V1 V2 or PV equals constant. Or P1V or 1.21050.5 or 6.010 N. 5a. State the values of the fixed points of a temperature scale. 0 degrees Celsius and 100 degrees Celsius. B.I. The graduations on a liquid and glass thermometer are equally spaced. For the equal spacing of the graduations to be correct, state 1. An assumption that is made about the liquid in the thermometer. Has capillary tube of constant cross-sectional area, diameter, radius, bore, width, thickness. 2. An assumption that is made about the structure of the thermometer. Has capillary tube of constant cross-sectional area, diameter, radius, bore, width, thickness. E. Liquid in glass thermometer A has a greater range than liquid in glass thermometer B. State one way the design of thermometer A is different from thermometer B. Compared with thermometer B, A has a capillary tube of greater cross-section, diameter, radius, width. E. Liquid in glass thermometer C has a greater sensitivity than liquid in glass thermometer D. State one way the design of thermometer C is different from thermometer D. Compared with thermometer D, C has capillary tube that is narrower, of smaller cross-section, thinner. C.I. In the space provided, draw a labeled diagram of a thermocouple thermometer. Diagram to show 3 wires labeled e.g. copper, iron, copper or with symbols for metals. OR metal A, metal B, metal A. 1 junction between different metals. Connections to voltmeter, ammeter, galvanometer identified by V, A, G, MV, Ma or arrow in a circle. E. Suggest when a thermocouple thermometer is more suitable than a liquid in glass. Thermometer. Measurement of a very higher, very low temperature or a rapidly varying temperature. Or a high range of temperature. If values given, more than 300 degrees Celsius, less than minus 200 degrees Celsius. 6. An electrical heater is placed on the floor of a room in a house. The heater is switched on. A. State the main process by which thermal energy is transferred to the air in all parts of the room. Convection. B. The heater has a power of 1.5 kilowatts. The air in the room has a mass of 65 kilogram. The specific heat capacity of air is 720 J kilogram degree C. I. Calculate the time it takes for this heater to raise the temperature of the air in the room from 8.0 degrees Celsius to 15.0 degrees Celsius. Time equals E equals McD or 65 times 720 times 7. 3.3 times 105 J. P equals ET in any form or T equals EP or 3.3 times 106 over 1.5 times 103. 220 S. E. State 2 reasons why the time calculated in BI is smaller than the actual time taken to raise the temperature of the air in the room from 8.0 degrees Celsius to 15.0 degrees Celsius. 2 of. The heater warms walls, floor, ceiling, windows, furniture, objects. Thermal energy conducted through walls, floor, ceiling, windows to exterior. Thermal energy used to raise temperature of air entering room via drafts, openings. 7a. In Fig. 7.1, the small circles represent molecules. The arrows refer to the change of state from the arrangement of molecules on the left to the arrangement of molecules on the right. Over. 7a. In Fig. 7.1, the small circles represent molecules. The arrows refer to the change of state from the arrangement of molecules on the left to the arrangement of molecules on the right. X, Y, Fig. 7.1. Complete the following by writing solid, liquid or gas in each of the blank spaces. 1. Change of state X is from solid. 2. Liquid. 2. Change of state Y is from liquid to gas vapor. B. Explain, in terms of the forces between their molecules, why gases expand more than solids when they undergo the same rise in temperature. Neighboring molecules of solid have strong forces of attraction between them. Gas molecules have no weak forces of attraction between them. Easier to increase separation of gas molecules than solid molecules. Gas expands more easily, so gas molecules move farther apart. C. A cylinder of volume 0.012 cubic meters contains a compressed gas at a pressure of 1.8 times 106 pascals. A valve is opened and all the compressed gas escapes from the cylinder into the atmosphere. The temperature of the gas does not change. Calculate the volume that the escaped gas occupies at the atmospheric pressure of 1.0 times 105 pascals. Volume equals 3. PV equals constant, or P1V1 equals P2V2. Or 0.012 times 1.8 times 106 equals V2 times 1.0 times 105. V2 equals 0.216 cubic meters, or 0.22 meters 3. Volume of escaped gas equals 0.220.012 equals 0.21 meters 3. 4.8 Define the specific latent heat of fusion of a substance. Thermal energy to change state. To melt solid per kilogram unit mass, not per degree Celsius. B. Small pieces of ice at 0 degrees Celsius are added to 0.35 kilograms of water. The initial temperature of the water is 24.5 degrees Celsius. The temperature of the water decreases to 0 degrees Celsius. The water loses 35,000 J of thermal energy as it cools. All of the ice added to the water melts. The specific latent heat of fusion of ice is 3.3 times 105 J kilogram. Calculate I. The specific heat capacity of water. Specific heat capacity equals 2. E equals mc delta T in any form, or C equals E per meter delta T. Or C equals 35,000 over 0.35 times 24.5. E. The mass of ice added to the water. Mass equals 3. C equals 4,100 J per kilogram degree C. 4 BII use of 35,000. E equals ml in any form, or m equals EL. Or 35,000 thirds 0.3 times 105. M equals 0.11 kilograms. 5a. Complete the sentences with words that describe the main process of thermal energy transfer. In each case, a man goes for a walk on a cold day. He touches a metal gate, which removes thermal energy from his hands by conduction. He holds the sides of a cup containing a hot drink. His hands gain thermal energy by conduction. Some farm workers have lit a fire. The man warms his hands by the side of the fire. His hands gain thermal energy by radiation. 3. B. Describe in terms of particles the transfer of thermal energy through the metal of the gate. After transfer from the man's hands, electrons move. Lattice molecular particle vibration, or W. T. E. Or free delocalized electrons. C. Fig. 5.1 shows a car on a sunny day in a hot country. The object labeled A is placed inside the windscreen. It is used by the owner of the car to reduce the temperature rise of the air in the car. Ring the most suitable material for the outer surface of object A. Explain your choice. Dull black, dull white, shiny black, shiny white. Explanation. 1. Shiny white. 2. Best reflector. 3a. Power station burns waste materials from farm crops to generate electricity. A. State and explain whether this process is renewable. Statement. Renewable, yes. Explanation. Crops can be regrown to replace resource. Waste materials don't run out. B. The power station uses some of its waste thermal energy to heat water for houses in a nearby town. State one problem of using waste energy in this way if the power station is far from the town. Water will cool too much, thermal energy lost during transfer. Suggest a way of reducing this problem. Lag. Insulate pipes or transport in a poor conductor of thermal energy. C. State 2 environmental consequences of burning coal to generate electricity. Ne2 from air pollution, harmful gases, acid rain. CO2, greenhouse gases, contribution to global warming. Not renewable. Damage from mining, drilling, or any valid environmental consequence of transport of coal. 3. Fig. 3.1 and Fig. 3.2 show how a puddle of water changes on a warm windy day. A. Describe the process by which the volume of water in the puddle decreases. Ne2 from. Amount of water in the pool decreases as water evaporates, becomes water vapor, gas. The more energetic molecules escape or faster molecules escape or molecules with more kinetic energy escape from the surface of the water. B. State and explain one change in the weather that would cause the volume of water in the puddle to decrease more slowly. Lower temperatures, colder day or less windy weather produces smaller pool more slowly because rate of evaporation decreases with decreasing temperature, or produces smaller pool more slowly as a draft over surface removes water vapor enabling faster rate of evaporation. C. Explain, in terms of molecules, how sweating helps to cool your body on a hot day. Ne3 from. Thermal energy in the skin, body transferred to molecules of sweat. These molecules have enough K to escape from the skin, become water vapor, leaving behind molecules with lower energy, which leaves the skin, body at a lower temperature. 4a. A sample of sand has a volume of 0.050 cubic meters. The density of the sand is 1,900 kilograms per cubic meter. The specific heat capacity of the sand is 1500 J kilogram degree C. I. Calculate the mass of the sample of sand. Mass equals 1900 times 0.05 equals 95 kilograms. M equals rho V in any form, or 1900 times 0.05. E. Calculate the thermal capacity of the sample of sand. Equals 95 times 1500 equals 140,000 J per degree Celsius, 1.4 times 105 J per degree Celsius. C equals M times C. E. The initial temperature of the sample of sand is 7.0 degrees Celsius. The sample of sand is heated using an electrical heater. The power of the heating element is 50 W. Calculate the time taken to increase the temperature of the sand to 19.0 degrees Celsius. Time equals 34,000 s 560 minutes 9h 20 minutes. Temperature rise equals 12 degrees Celsius 19 to 7. Or, E equals C times delta theta in any form. T equals EP in any form, or thermal capacity times 12/50. B. In some countries, the soil is too cold for plants to grow well. In these countries, plants are grown in plastic pots and kept inside. The pots, containing soil, are placed on sand. The sand is heated using an electrical heater, as shown in Fig. 4.1. I. Describe, in terms of molecules, how thermal energy is transferred from the heated sand through the base of the plastic pot. Sand molecules gain K or vibrate more or hit other molecules when heated. Thermal energy is transferred by conduction. Energy is transferred to molecules of plastic pot in contact with sand through collisions. Energy or lattice vibrations transferred to neighboring molecules. E. The heating element in Fig. 4.1 remains switched on. The temperature of the sand remains constant at a value above room temperature. Explain why the temperature of the sand remains constant. Sand is warmer than surroundings, and so thermal energy constantly is lost from the sand. At a constant temperature, rate of thermal energy supplied to the sand is equal to rate of thermal energy lost from sand. 4 Fig. 4.1 shows a metal pan on an electric hotplate. The pan contains 200 cc of water. The pan is heated. The temperature of the water in the pan increases. A. Thermal energy is transferred through the metal pan by conduction. State and explain the two ways that thermal energy is conducted in a metal. Delocalized, free, mobile electrons. Electrons move through metal, or electrons collide with distant particles, or electrons carry energy through the metal. Lattice vibrations transfer energy to neighboring particles, or particles vibrate and cause nearby, adjacent particles to vibrate, or vibrating particles collide with particles transferring energy. B. I. The water boils and leaves the liquid as a gas. Explain, in terms of forces and distances between particles, why the gas occupies a much greater volume than it does as a liquid. Attractive forces between particles are much greater in liquids than in gases. Particles in gases are much further apart than in liquids. E. State two ways in which boiling differs from evaporation. Occurs at a fixed temperature. Takes place throughout the liquid. C. The water is replaced with 200 cc of milk. The initial temperature of the milk is 20.0 degrees Celsius. The boiling point of milk is 95.0 degrees Celsius. The milk starts to boil when 60,700 J of thermal energy has been transferred to it. The density of milk is 1.03 grams per cc. Calculate the value of the specific heat capacity of milk. Give your answer to three significant figures. 3.93 J per gram degree C or 3930 J per kilogram degree C. Equals M, V or M equals V or 1.03 200 or 216. C equals E per meter delta or C equals E per meter delta or 60 and 700 206 75 or 60,700 over 1.0320075. M equals 206 grams or delta equals 75 degrees Celsius. 0625_S19_Ms_41.pdf. 4 gas of mass 0.23 grams is trapped in a cylinder by a piston. The gas is at atmospheric pressure, which is 1.0 times 105 pascals. Fig. 4.1 shows the piston held in position by a catch. The volume of the trapped gas is 1.9 times 10 to 4 m3. An electrical heater is used to increase the temperature of the trapped gas by 550 degrees Celsius. The specific heat capacity of the gas is 0.72 G degree C. Calculate the energy required to increase the temperature of the trapped gas by 550 degrees Celsius. E equals mc increment T in any form words, symbols or numbers or E equals mc increment T, or 0.23, times 0.72, times 550, 91 J. The power of the heater is 2.4 W. 1. Calculate how long it takes for the heater to supply the energy calculated in AI. Time equals 2, 1. T equals EP in any form words, symbols or numbers or T equals EP or 91/2.4. 38 s. 2. In practice, it takes much longer to increase the temperature of the gas by 550 degrees Celsius. Using the heater. Suggest one reason for this. Thermal energy is used to increase the temperature of lost to cylinder piston heater surroundings. B. When the temperature of the gas has increased by 550 degrees Celsius, its pressure is 2.9 times 105 pascals. The catch is then released, allowing the piston to move. As the piston moves, the temperature of the gas remains constant. State and explain what happens to the piston. Piston moves to the right away from heater or accelerates to right. Pressure of gas greater, pressure greater on left, resultant force to right. Determine the volume of the gas when the piston stops moving. Volume equals 2. V2 equals P1 V1 P2 in any form or V2 equals P1 V1 P2, or 2.9 times 105 times 1.9 times 10⁻⁴ over 1.0 times 105, 5.5 times 10 to 4. 5 liquids and gases are two states of matter. In both boiling and evaporation, a liquid changes into a gas. State 2 ways in which boiling differs from evaporation. Any 2 from occurs throughout the liquid or bubbles formed, occurs at one temperature, boiling point, does not produce cooling or unaffected by draft, surface area, humidity. Before injecting a patient, a doctor wipes a small amount of a volatile liquid onto the patient's skin. Explain, in terms of molecules, how this procedure cools the patient's skin. More energetic molecules escape from the liquid, or molecules gain energy and escape. Or molecules overcome intermolecular forces, break bonds. Average speed decreases, or molecules with less kinetic energy left behind. Temperature of liquid decreases, thermal energy conducted, gained from skin, body, or thermal energy lost by skin, body. Gases can be compressed but liquids are incompressible. Explain, in terms of molecules, why liquids are incompressible. Molecules touching or no space between molecules. Large repulsive intermolecular forces when moved closer. 0625_S19_Ms_42.pdf. 5. A liquid is heated so that bubbles of its vapor rise to the surface and molecules escape to the atmosphere. State the name of this process. Boiling. 1. At a lower temperature than in AI, molecules escape from the surface to the atmosphere. State the name of this process. Evaporation. 1. Fig. 5.1 shows apparatus used to determine the power output of a heater. The metal block has a mass of 2.7 kg. The metal of the block has a specific heat capacity of 900 J kg degree C. In 2 minutes 30 s, the temperature of the block increases from 21 degrees Celsius to 39 degrees Celsius. Calculate the power of the heater. Power equals 4 E equals mc. Increment T in any form, or E equals mc. Increment T, or E equals 2.7 times 900 times 18, 44,000 J. E equals PT in any form, or P equals ET, or P equals 43 and 741/150ths. P equals 290 W. E. State and explain a precaution that can be taken to improve the accuracy of the experiment. Lagging insulation, named insulator around, on block. Reduction of thermal energy, heat losses. 0625_S19_Ms_43.pdf. 4a. Water molecules escape to the atmosphere from water boiling in a pan. Water molecules evaporate from the surface of a bowl of cool water and also escape to the atmosphere. State 2 ways in which boiling is different from evaporation. Any 2 from bubbles form or occurs throughout liquid. Only occurs at one temperature, boiling point. Does not produce cooling or not affected by surface area, humidity, draft, or does not lower K of molecules left in the liquid. B. Fig. 4.1 shows a heater in a metal block. The power of the heater is 370 W and it is switched on for 4.0 minutes. The metal block has a specific heat capacity of 420 J kilogram degrees C and a mass of 5.0 kilogram. Calculate the increase of temperature of the block. Assume all the thermal energy from the heater is transferred to the block. Temperature increase equals 4 E equals PT in any form, or E equals 370 times 240 equals 89,000 J. E equals mc. Increment T in any form. Temperature increase equals 89,000 5.0 times 420 equals 42 degrees Celsius. 5 Fig. 5.1 shows a cross-section of the inside of a vacuum flask containing a cold liquid. The walls of the vacuum flask are made of glass. A. The vacuum flask is being used to keep a liquid cool on a hot day. Explain how the labeled features of the vacuum flask keep the liquid cool by reducing thermal energy transfer. Include the names of the processes involved. Any mention of radiation, infrared radiation, WRT. Silvered surfaces. Silvered surfaces are poor emitters, poor absorbers, good reflectors. Glass is a poor conductor, or glass reduces thermal energy, heat gain by conduction. Vacuum prevents thermal energy, heat gain by conduction or convection. Stopper reduces thermal energy, heat gain by convection. B. Suggest a suitable material for the stopper. Any suitable insulator, e.g. cork, plastic, rubber. 0625_S20_Ms_41.pdf. 4 Water has a specific heat capacity of 4,200 J kilogram degrees C and a boiling point of 100 degrees Celsius. A. State what is meant by boiling point. Temperature at which liquid turns into gas. B. A mass of 0.30 kilograms of water at its boiling point is poured into a copper container which is initially at 11 degrees C. After a few seconds, the temperature of the container and the water are both 95 degrees Celsius. I. Calculate the energy transferred from the water. Energy transferred equals 2 E equals mc delta T, or 0.30 times 4,200 times 100, 95, 6,300 J. E. Calculate the thermal capacity of the copper container. Thermal capacity of the copper container equals 2 C equals E delta T, or 6,384ths, 75 J per degree Celsius. E. Water from the container evaporates and the temperature of the remaining water decreases slowly. Explain, in terms of molecules, why evaporation causes the temperature of the remaining water to decrease. Molecules do work against attractive force as they evaporate. More energetic molecules more likely to escape. Average energy of remaining molecules decreases. 0625_S20_Ms_42.pdf. 3a. A solar panel receives energy from the sun at a rate of 5.0 kilowatts. Thermal energy is transferred from the solar panel to water with an efficiency of 20%. Cold water of mass 15 kg enters the solar panel every hour. The specific heat capacity of water is 4,200 J kilogram degrees C. Calculate the temperature increase of the water. Temperature increase equals Degree C, 4. E equals mc delta T in any form or E equals mc delta T. Efficiency equals energy output, energy input in any form. 15 times 4200 times delta T equals 5000 times 3600 times 0.2. Delta T equals 5000 times 3600 times 0.2 times 4200 equals 57 degrees Celsius. B. State and explain one advantage and one disadvantage of heating the water in a solar panel, compared with heating the water in a coal-burning boiler, e.g. renewable or no air pollution or low running costs or no named polluting gas or no greenhouse effect. Explanation that follows from advantage stated, e.g. expensive to install or not available at night or visual pollution or needs a suitable roof space. Explanation that follows from disadvantage stated. 4 Fig. 4.1 shows a liquid in glass thermometer without a temperature scale. The liquid inside the thermometer has a melting point of -39 degrees Celsius. A. Describe simple experiments to mark the positions of the fixed points on this liquid in glass thermometer. Place in melting ice. When bead has stopped moving or mark as lower fixed point, 0 degrees Celsius. Place in steam above boiling water. When bead has stopped moving or mark as upper fixed point, 100 degrees Celsius. B. A scientist is measuring temperatures at the South Pole. These temperatures have a minimum value of -90 degrees Celsius. State why the liquid used in the thermometer in Fig. 4.1 would not be suitable for this scientist. Bead would not be liquid. C. State a design change that I. Increases the sensitivity of a liquid in glass thermometer. Thinner bore tube. Smaller bulb or use liquid which expands more per unit change in temperature. E. Increases the range of a liquid in glass thermometer. Longer tube. Larger volume glass bulb. Use liquid which expands less per unit change in temperature. D. State the property of the liquid which ensures that the scale on a liquid in glass thermometer is linear. Expands uniformly with temperature. Same distance between all degree intervals. 0625_S20_Ms_43.pdf. 4.8 Describe, in terms of molecules, what happens when a liquid evaporates. Molecules escape from the surface of the liquid. More energetic, faster moving molecules escape. Slower, less energetic molecules are left behind. Temperature of liquid decreases because average Ke of remaining molecules is lower. B. Fig. 4.1 shows wet clothes drying on a washing line in an outside area. Washing line. Fig. 4.1. State 2 changes in the weather that help the wet clothes to dry more quickly. Any 2 from. Air temperature increases. More wind. Cloud stops covering the sun. 5.8 Fig. 5.1 shows a plastic cup. The cup contains sand, an electric heater and a thermometer. Temperature of the sand is 20 degrees Celsius. The heater is switched on for 2.0 minutes. The temperature is recorded until the temperature stops increasing. The highest temperature recorded by the thermometer is 33 degrees Celsius. I. Calculate the energy supplied by the heater. Energy equals 2. E equals PT in any form. E equals 6000 J. E. Calculate a value for the specific heat capacity of the sand, using your answer to AI and the data in the question. Specific heat capacity equals 3. E equals mc delta T in any form. 6550 33 to 20. C equals 0.84 J per gram degree C or 840 J per kilogram degree C. E. Explain why the specific heat capacity of sand may be different from the value calculated. In A.E. either sum of energy supplied by the heater heats the heater, goes to lagging, goes to surroundings. Specific heat capacity is lower than value in E. Some energy may be absorbed from surroundings if they are at a higher temperature. Specific heat capacity is higher than value in E. B. On a sunny day, the temperature of the sand on a beach is much higher than the temperature of the sea. Explain why. Specific heat capacity of water is much higher than specific heat capacity of sand. Same rate of energy supplied to sand and sea. C. Draw a labeled diagram to show the structure of a thermocouple thermometer. Cold junction labeled or shown in ice or something similar. Diagram with 2 junctions with voltmeter labeled. 2 different metals labeled. Galvanometer or voltmeter joining ends of wires. 0625_S21_Ms_41.pdf. 4. An aluminium saucepan with a plastic handle contains cold water. Fig. 4.1 shows the saucepan on a hot plate. Fig. 4.1. A. State why the pan is made from aluminium but the handle is made from plastic. Aluminium is a good conductor of heat and plastic is a poor conductor. Does not conduct heat. B. The hot plate is switched on and, as the temperature of the water increases, the internal energy of the water increases. I. State, in terms of molecules, what is meant by an increase in internal energy. Increase in kinetic energy of molecules. Increase in potential energy of molecules. E. Explain, in terms of the atomic lattice and electrons, how thermal energy is transferred through the aluminium. Ne3 from atoms touching the hot plate lattice vibrate faster. Atoms pass on energy vibration to neighboring atoms to other atoms by collision. Atoms pass on energy to electrons. Electrons hit distant atoms or electrons move through lattice. E. Eventually, the water reaches boiling point. Thermal energy from the hot plate is still being transferred to the water. Explain, in terms of molecules, the effect of this thermal energy on the water. Molecules escape from the liquid as a vapor. Bonds broken, attractive forces overcome. Molecules gain potential energy, or work done to separate molecules, break bonds, overcome forces. IV. The mass of the water decreases by 0.11 kilograms in 300 s. The specific latent heat of vaporization of water is 2.3 times 106 J kilogram. Calculate the rate at which the water gains thermal energy. Rate of gain of energy equals 340 W. E equals mLV in any form or 0.11 times 2.3 times 106 or 2.53 times 105. Rate equals mLVT in any form or 0.11 times 2.3 times 106 300ths or 2.53 times 105 300ths. 5. Fig. 5.1 shows the structure of a liquid in glass thermometer. Fig. 5.1. The bulb of the thermometer is placed into a beaker of warm water. As the liquid expands, it moves along the tube. A. Explain, in terms of molecules, why a liquid expands when heated. Molecules, they speed up or gain kinetic energy. Molecules move further apart or push others away. B. Explain, in terms of molecules, why a liquid expands more than a solid when heated. Forces between liquid molecules weaker than in solids. Less energy work done to separate molecules or greater separation for same work done, same increase in energy. C. A second thermometer has a larger bulb that contains more of the same liquid than the thermometer shown in Fig. 5.1. It has a different scale. In every other way, it is identical. I. Explain how the sensitivity of the second thermometer compares with the sensitivity of the thermometer in Fig. 5.1. Greater sensitivity. Volume increase of liquid in second thermometer is greater. Or liquid moves a greater distance for the same temperature increase. E. Explain how the range of the second thermometer compares with the range of the thermometer in Fig. 5.1. Smaller range in either of. Smaller temperature increase for liquid meniscus to reach end of tube. Expands more, greater sensitivity and tube of same length. D. I. State one everyday problem that is a result of thermal expansion. Statement of problem e.g. bridges buckle in hot weather. E. Suggest and explain one way of solving this problem. Suggested solution to problem stated in 5D e.g. allow gaps at the ends of the bridge. More detail e.g. as the bridge expands the gaps close. 0625_S21_Ms_42.pdf. 4a. Pollen particles are mixed into a liquid. They are seen to move when observed through a microscope. I. Describe this movement. Random, haphazard, zigzag, irregular. E. Explain this movement in terms of the molecules of the liquid and the pollen particles. Liquid water molecules move fast or pollen particles massive. Collide, bombard. Uneven collisions. Collisions from different directions cause random movement or liquid water molecules move randomly. B. I. Medical professionals sometimes rub ethanol over the skin of a patient. Ethanol evaporates readily at room temperature and has a high specific latent heat of vaporization. State whether the patient experiences heating, cooling or neither at the site where the ethanol is applied. Explain your answer. Cooling. Thermal energy used needed to evaporate ethanol, overcome attractive forces between molecules, particles. Thermal energy taken from skin, patient, person. Alternative route for last 2 meters. P. S. More, most energetic liquid molecules particles escape or less, least energetic liquid remain. Less, least energetic molecules particles linked to lower temp of skin. E. State any effect on the rate of evaporation of ethanol when a fan blows air over the patient's skin. Greater, increases, faster, higher. 5a. A machine delivers a hot drink in a plastic cup, which is uncomfortably hot to hold. Fig. 5.1 shows the cup with the hot drink. Fig. 5.2 shows the cup with the hot drink and a holder for the sides of the cup. Fig. 5.2b shows a cross-section through the holder. The holder is made from 2 strong paper cylinders separated by a wavy piece of strong paper to make air gaps. Explain how using the holder makes it more comfortable to hold the cup. Air, good insulator, poor conductor. Holder, it stops, reduces conduction. No, less thermal energy conducted to hand. Temperature of outside of holder lower than cup or less energy to skin, hand, person. B. A student carries out experiments on the cooling of the hot drink described in A with and without the holder in place. He finds that the holder only reduces the rate of cooling slightly. Suggest and explain another action that reduces the rate of cooling more effectively. Put a lid cover on cup. Mention of convection. Less, no. Convection from surface. Alternative route for last 2 meters. P. S. Mention of evaporation. Less, no evaporation from surface container. C. State the method of thermal energy transfer from a star through the vacuum of space. Radiation. 0625_S21_Ms_43.pdf. 4a. I. Define specific latent heat of fusion. Energy transferred when 1 kilogram unit mass of a substance freezes or melts. Energy transferred when a substance freezes, melts, changes state. E. A cup of water contains 250 cc of water at a temperature of 0 degrees Celsius. An identical cup contains 250 cc of a mixture of ice and water at a temperature of 0 degrees Celsius. The temperature of the surrounding air is 20 degrees Celsius. State and explain which cup contains the liquid with the lower temperature after 10 minutes. Cup containing mixture of ice and water. Mixture of ice and water will remain at 0 degrees Celsius until all ice is melted, but temperature of water at 0 degrees Celsius rises, or reverse argument, or energy needed for change of state so temperature doesn't rise until this has taken place. B. I. On a hot day, sweat forms on a person's skin and then evaporates. Explain, in terms of molecules, how the evaporation of sweat cools the person. In evaporation, more energetic, faster-moving molecules with higher kinetic energy escape from surface. Lower energy, slow molecules remain, or so remaining liquid is cooler. Thermal energy is taken from person to liquid so person cools down. E. Explain why this process is more effective when a wind is blowing. Greater, faster evaporation of sweat as wind blows fast-moving molecules away, or molecules do not re-enter the liquid. 0625_S22_Ms_41.pdf. 3. During a picnic on a warm, dry day, a metal can of lemonade is wrapped in a damp cloth. Evaporation cools the water in the cloth. A. Explain, in terms of molecules, how evaporation cools the water in the cloth. Faster, higher speed, more energetic molecules escape into air. Average speed, average kinetic energy of molecules decreases. Temperature related to speed, energy of molecules are slower, lower speed, less energetic molecules remain in water. B. As the water in the cloth cools, so does the lemonade. Explain how electrons transfer thermal energy through the metal of the can. Ne3 from atoms, ions vibrate. Vibrating atoms, ions hit electrons. Electrons propelled, traveling through metal, moving through metal. Electrons hit distant atoms. Free electrons, delocalized electrons mentioned. 4a. Thermocouple is a device that is used as a thermometer. A. Fig. 4.1 shows a beaker that contains molten sulfur at an initial temperature greater than 400 degrees Celsius. I. On Fig. 4.1, sketch and label a diagram of a thermocouple that is used to determine the temperature of the sulfur as it cools to room temperature. 3 wires of at least 2 different metals. 1 junction in sulfur. The other junction in ice-water mixture, at room temperature, and one of the wires must be from the first junction. Labeled voltmeter, voltmeter symbol correctly connected. E. Describe briefly how the temperature of the sulfur in the beaker is deduced. Measure electromotive force. How to find temperature from electromotive force, e.g. use calibration graph or calculation or table. B. State one advantage of using a thermocouple to measure temperature rather than using a liquid and glass thermometer. Measures high temperatures. Wires do not melt. Rapid response. Robust. Small heat capacity. Electrical output. Can be remote from observer, direct input to computer. 5 Fig. 5.1 shows a kitchen tap that supplies instant boiling water. Cold water passes over an electric immersion heater inside the tap. The boiling point of water is 100 degrees Celsius. A. State what is meant by boiling point. Temperature at which liquid becomes a gas or liquid and gas exist together. B. The immersion heater is powered by the mains at a voltage of 230 V. When the tap is opened, the heater switches on and the current in the heater is 13 A. I. Calculate the thermal energy produced by the heater in 60 S. Thermal energy equals 2. 1.8. 105 J. E equals VIT in any form or 230. 13. 60 or 230. 13 or 3000. E. The specific heat capacity of water is 4200 J kilogram degree C. The cold water that enters the tap is at 22 degrees C. Calculate the rate at which water at its boiling point emerges from the tap. Rate equals 4. 9.110 to 3 kg per second, 9.110 to 3 kg per second. T equals 100 to 22 or 78 or T equals 100 to 22 or 78. M equals E quart in any form or 1.8 105 4278 or rate equals P quart in any form or M equals E quart and E equals PT 1.8 105 4278 60 or 5.510 N or 9.1 9.210 N or 3000 4278 or 230 and 13 4278 or 9 1/9.210 N. C. The metal tap is earthed and there is a fuse in the cable that connects the heater to the mains. If the tap becomes live or if the live cable touches the metal tap, there is a current to earth in the earth wire which blows the fuse. The current in earth wire is large and fuse melts, blows, stops current, breaks circuit. 6 Fig. 6.1 shows a road next to the sea. A. On a sunny day, the sun warms the road. Describe how energy from the sun reaches the earth and warms the road. Ne3 from radiation, light, infrared, electromagnetic radiation. Travel through space, vacuum. Absorbed by road. B. The temperature of the road is greater than the temperature of the sea. The surface of the road is black. Suggest one reason why the temperature of the road is greater than that of the sea. Road black surfaces are good absorbers of radiation, or sea is a poor absorber of radiation. C. The air above the road is heated by the warm road. I. Describe how this affects the molecules of the air. They molecules speed up or gain kinetic energy. They molecules move further apart. E. A cyclist traveling along the road notices that a cool breeze is blowing from the sea to the land. Explain how convection produces this breeze. You may include a diagram if it helps your answer. Density of air above road decreases or density of hot air decreases. Air above land road rises or air that is hot rises. Air above road replaced by cool air, air from above sea. 0625_S22_Ms_42.pdf. 1 Fig. 1.1 shows an electrically powered bicycle. When fully charged, the battery can deliver a power of 600 W for 60 minutes. I. Calculate the energy, in joules, stored in the battery when fully charged. Energy equals J, 3. E equals 2,200,000 J or 2.2. 106 J. E equals PT in any form. E equals 600. 3600. E. State the form of energy stored by the battery. Chemical, 1. B. The bicycle has a motor with an electrical input power of 250 W. Calculate the time for which the battery can power the bicycle. Time equals 2. T equals 8600 S or 140 minutes or 2.4. H or 2H 24 minutes. Or T equals 8800 S or 147 minutes or 2H 27 minutes. T equals 2.2. 106 250ths or 600. 60 250ths or 1. 600 250ths. C. Consider this bicycle compared to a small motorcycle. State 2 environmental benefits of the electrically powered bicycle. Any 2 from less noise or no noise. Less or no air gaseous pollution from the bicycle or does not produce acid rain. The bicycle uses no less fossil fuel. Does not contribute to greenhouse effect or does not release CO2. 4a. State and explain the 2 features of a liquid and glass thermometer that are necessary for linearity. Statement. Bore of constant cross-sectional area. Explanation. Idea of same movement, change in length of liquid thread. And for same increase in volume, expansion of liquid. Statement. Liquid has constant thermal expansion. Explanation. Liquid moves same distance for each degree C temperature rise. B. The value of the heat capacity of the hot junction of a thermocouple thermometer is important in ensuring that it can measure temperature changes very rapidly. Explain why. Heat capacity, it is small. Only needs a small amount of thermal energy to raise its temperature. C. The hot junction of a thermocouple thermometer has a heat capacity of 0.11 J per degree Celsius. Calculate the thermal energy required to increase the temperature of the hot junction from 20 degrees Celsius to 345 degrees Celsius. Energy equals 336 J. E equals CT in any form. E equals 0.11. 345 to 20 or T equals 325 degrees Celsius. 0625_S22_Ms_43.pdf. 4a. Fig. 4.1 shows apparatus used to observe the motion of smoke particles, Brownian motion. The glass cell has light shining on it from the side. The smoke particles are seen as bright specks of light when looking through the microscope. I. Draw the path of one of the bright specks of light. Zigzag motion. Random changes of direction. Random length of path in each direction. E. Explain, in terms of forces and the motion of air molecules, the cause of the motion of the smoke particles. Any 4 from air molecules bombard smoke particles. Air molecules are small compared to smoke particles, have smaller mass. Air molecules are very fast moving. Air molecules move in random directions. Collisions exert unbalanced forces on smoke particles. B. The temperature of the air in a sealed glass container is increased. I. Explain, in terms of molecules, why the internal energy of the air increases. Kinetic energy and potential energy of molecules increase, hence internal energy increases. E. Explain, in terms of molecules, why the pressure of the air also increases. Bigger change in momentum of molecules. Molecules hit the walls harder. Molecules hit more often, more frequently. 5a. Define specific heat capacity. Energy required to raise the temperature of 1 kilogram 1 gram unit mass of a substance by 1 degree Celsius unit temperature. Energy required to raise the temperature of a substance by 1 degree Celsius. B. A bowl contains 500 cc of water at a temperature of 5.0 degrees Celsius. The bowl of water is placed in a freezer for several hours. When the bowl is removed from the freezer, it contains ice at a temperature of minus 18.0 degrees Celsius. The density of water is 1000 kilograms per cubic meter. I. Calculate the mass of water in the bowl when it is placed in the freezer. Mass equals 0.50 kilograms equals mv in any form. E. The specific heat capacity of water is 4200 J kilogram degree C. The specific heat capacity of ice is 2100 J kilogram degree C. The specific latent heat of fusion of water is 3.3 times 105 J kilogram. Calculate the energy given out as the water cools from 5.0 degrees Celsius to ice at minus 18.0 degrees Celsius. Energy equals 190,000 J 1.9. 105 J 190 kilojoules. E equals mc increment T in any form. E equals ml in any form. Use OFC equals 4200 J per kilogram degree C. And increment T equals 5. Use OFC equals 2100 N. Increment T equals 18. 0625_S23_Ms_41.pdf. 3a rubber balloon is inflated with helium and sealed so that no helium escapes. The balloon is positioned immediately below the ceiling in a room. Heaters are switched on and the temperature of the air in the room increases. A. When the heaters are first switched on, the temperature of the air immediately below the ceiling increases more quickly than the temperature of the air in the rest of the room. Explain why this happens. Heated, hotter, warmer. Air is less dense or cooler air is more dense. Heated, hotter, warmer air rises to ceiling displacing cooler air or cooler air falls displaced by warmer air. B. The temperature of the helium in the balloon increases, and as the rubber stretches, the volume occupied by the helium increases. I. State what happens to the motion of the helium particles as the temperature increases. Speed, velocity of particles increases or they move faster. E. As the rubber stretches and the volume of the helium increases, the pressure of the helium remains constant. Explain, in terms of the particles of helium, how the pressure of the helium remains constant. Higher temperature means particles collide with rubber harder, with more force, with greater momentum change. Larger volume means particles collide with rubber less frequently. Larger volume means larger surface area for particle collisions. Effect of larger volume cancels effect of increased temperature. The effect of larger area cancels the effect of larger force. P equals F A, so the two changes cancel each other. 4a student investigates the efficiency of a filament lamp. Fig. 4.1 shows the filament lamp with its glass bulb immersed in water in a beaker. The reading on the thermometer in the water is 19.0 degrees Celsius. Only the glass of the lamp is in contact with the water and the electrical connections are completely insulated. The lamp is switched on. At the end of the experiment, the temperature of the water is 21.5 degrees Celsius. A. The mass of the water in the beaker is 600 grams and the specific heat capacity of water is 4,200 J kilogram degree C. I. Show that the increase in the internal energy of the water is 6,300 J. C equals increment E per meter increment or increment E equals Mc increment. Increment equals 21. 5 to 19 or increment equals 2.5 degrees Celsius. Increment E equals 0.6042002.5 or increment E equals 0.604221, 5 to 19. E. In the experiment, the lamp is switched on for 500 S. The power supplied to the filament lamp is 13 W. The useful energy from the lamp is transferred as light. The energy that increases the temperature of the water is wasted energy. Determine the maximum possible efficiency of the filament lamp. Maximum possible efficiency equals 4. Maximum possible efficiency equals 3.1% or 0.031. E equals PT or E equals PT or E equals 13,500 or E equals 6,500. Efficiency equals useful energy output, total energy input 100%. Or efficiency equals useful energy output, total energy input 100%. Or efficiency equals 6500, 6300, 6,500. Or efficiency equals 206,500's 100%. Or P equals ET or P equals ET or P equals 6 and 300/500ths or P equals 12.6 W. Useful power output equals total power output, wasted power output. Or useful power output equals 13, 6,300/500ths. Or useful power output equals 13 minus 12.6. Efficiency equals useful power output, total power input 100%. Or efficiency equals useful power output, total power input 100%. Or efficiency equals 0. 4/13,100ths%. B. The efficiency of the lamp is less than the value determined in AE. Suggest one reason for this. Any one from. Temperature change is an underestimate due to thermal energy losses. Thermal energy is transferred from the water to air, beaker, bench. Energy other than light transferred in lamp filament glass internal structure. Some water evaporates. 10 Pluto is a dwarf planet. Fig. 10.1 shows the direction of motion of Pluto as it follows its elliptical orbit around the Sun. A. Point X is the point in the orbit closest to the Sun and point Y is the point furthest away. The orbital speed of Pluto varies as it orbits the Sun. I. Describe how the speed of Pluto varies as it moves from X to Y and then back to X. Speed decreases from X to Y and then increases from Y to X. E. Explain, in terms of energy transfers, why the speed of Pluto varies in this way. Ne3. From gravitational potential energy GPE transfers to kinetic energy K or vice versa. K transfers to GPE from X to Y and GPE transfers to KE from Y to X. Speed decreases as KE decreases, or most GPE at Y or least GPE at X. Total of GPE plus K energy is constant. B. The average temperature on the surface of Pluto is 43 K. I. Convert this temperature to a value in degrees Celsius, degree C. Temperature equals minus 230 degrees Celsius. E. Pluto has a white surface, as shown in Fig. 10.2. As Pluto rotates, the white surface alternately faces towards and away from the Sun. Explain how this affects the temperature of Pluto as it rotates on its own axis. White surface is a poor absorber, good reflector, poor emitter of IR radiation. Black other surface is a good absorber, poor reflector, good emitter of IR radiation. Any one from. The white surface increases in temperature less when facing the Sun. The white surface decreases in temperature less when facing away from Sun. The black other surfaces increases in temperature more when facing the Sun. The black other surface decreases in temperature more when facing away from Sun. Less variation in temperature on white surface during one whole rotation. 0625_S23_Ms_42.pdf. 4.8 The temperature of a fixed mass of gas at constant volume is decreased. State and explain, in terms of particles, how the pressure of the gas changes. Pressure decreases and particles have smaller velocity, momentum, smaller EK, kinetic energy when temperature is lower. Lower rate, frequency of collision of particles. Particles collide with smaller force or smaller impulse change. B.I. State the value of absolute zero in degree C. Value of absolute zero equals minus 273 degrees Celsius. E. Explain what is meant by the term absolute zero. Refer to particles in your answer. Temperature at which particles have least EK, kinetic energy. Lowest possible temperature. C. Cylinder 1 contains 350 cc of gas at a pressure of 9.0 times 104 pascals. The gas is transferred to cylinder 2 and the pressure increases to 1.6 times 105 pascals. The temperature remains constant. Calculate the volume of cylinder 2. Volume equals 200 cc. PV equals constant or 9.0 104,350 equals 1.6105 V2. V2 equals 9.0 104,350, 1.6105 or V2 equals 2.010 N or 1.9710 N. 5.8 Fig. 5.1 shows an electric heater used to heat a room. The dimensions of the room are 4.5 meters times 6.1 meters times 2.4 meters. The density of air is 1.2 kilograms per cubic meter. I. Show that the mass of air in the room is 79 kilogram. Equals m, v or m equals v. M equals 1.24.56.12.4 equals 79 kilogram or m equals 79.056 kilograms. E. The power of the heater is 1100 W. The specific heat capacity of air is 1000 J kilogram degree C. Calculate the time taken to increase the temperature of the air in the room from 16.0 degrees Celsius to 20.0 degrees Celsius. Time equals 290 s. C equals increment E per meter increment or increment E equals Mc increment or increment E equals 79 1004.0 or increment E equals 316,000 or increment equals 4.0. P equals increment E T or increment E equals PT or increment E equals 1100 T. T equals Mc increment P or T equals 79 1004. 0 1100ths or T equals 316,000 1100ths. E. Suggest one reason why the time calculated in AE is the minimum time needed to increase the temperature of the air in the room from 16.0 degrees Celsius to 20.0 degrees Celsius. Any one from. Thermal energy is transferred to furniture, walls, objects in the room. Thermal energy is transferred through windows, doors, floor, ceiling, from the room. B. Fig. 5.2 shows a cross-section of a double-glazed window in the room. State the main methods of thermal energy transfer from the room to outside which are reduced by this type of window. Conduction and convection. 0625_S23_Ms_43.pdf. 3.ai. State which state of matter, solid, liquid or gas, has the greatest thermal expansion and which has the least. Greatest. Gas. Least solid. E. Describe, in terms of the motion and arrangement of particles, the structures of solids. And gases. Ne3 from. Solids particles vibrate. Gases particles move freely. Solids particles in fixed close positions. Gases particles randomly arranged in container wide separation. Gas particles move quickly. Bi. Define specific heat capacity. Specific heat capacity is the energy required to raise 1 kg unit mass by 1 degree Celsius 1 K 1 Kelvin unit temperature. Energy required per unit mass 1 kg. Or energy required per unit temperature 1 degree Celsius increase 1 K increase 1 Kelvin increase. E. A student carries out an experiment to determine the specific heat capacity of a metal. A. Cylinder of the metal is heated by a 12W electrical heater. State the readings that the student takes. Time, mass, initial temperature and final temperature. 0625_W19_Ms_41.pdf. 0625_W19_Ms_42.pdf. 4a. A student carries out an experiment to determine the thermal capacity of a metal block. The block is heated by an electric heater for 23 minutes. The current in the heater is 3.0 A at a potential difference P. D. of 12 V. The temperature of the block rises from 20 degrees Celsius to 70 degrees Celsius. Calculate the thermal capacity of the block. Thermal capacity equals 4A E equals VIT in any form, or E equals VIT. Or E equals 3 times 12 times 23 times 60. E equals 50,000 J. C equals E increment T in any form, or C equals E increment T. Or C equals 49 and 680 fiftieths, or 50,000 fiftieths. C equals 990 J per degree Celsius. B. Two metal spheres of different diameters are heated to 900 degrees Celsius in a hot oven. The two spheres are removed from the oven. 1. State and explain any difference in the initial rates of emission of radiation of thermal energy between the two spheres. Larger sphere emits, radiates, loses thermal energy more. Greater surface area. 2. One hot sphere is now heated in a hotter oven. State and explain any effect on the rate of emission of radiation of thermal energy from that sphere when it is removed from the hotter oven. Greater rate of radiation. 0625_W19_Ms_43.pdf. 4. Solids have a fixed shape. Liquids adapt to the shape of their container. Gases fill their container. Explain in terms of forces between molecules and arrangement of molecules, why solids, liquids and gases have these properties. Solids. Molecules in lattice arrangement. Strong forces between molecules. Liquids. Molecules not fixed in place, or molecules have an irregular arrangement. Molecules slightly further apart on average than in solids, or spaces between the molecules. Average forces too weak to keep molecules in a definite pattern, or forces just enough to hold molecules in the bulk of the liquid. Gases. Molecules far apart. Weak, no forces between molecules except during collisions. 5. An electric kettle contains water at a temperature of 19 degrees C. The kettle has a power rating of 3.0 kilowatts and is switched on for 3.5 minutes. A. Calculate the energy supplied to the kettle by the electricity supply. Electrical energy equals 3. Energy equals power x time in any form equals 3000 times 3.5 times 60 equals 630,000 J. B. At 3.5 minutes, the temperature of the water reaches 100 degrees Celsius. The volume of the water in the kettle is 1700 cc and its density is 1.0 grams per cc. The specific heat capacity of water is 4200 J kilogram degree C. Calculate the thermal energy gained by the water. E equals mc increment T in any form. M equals 1700 1,000ths. Increment T equals 100 to 19, or increment T equals 81. E equals 1700 1000 times 4200 times 81 equals 580,000 J. C. Calculate the efficiency of the kettle. Efficiency equals useful energy output total energy input, or 580,630,000 times 100 equals 0.92 or 92%. 0625_W20_Ms_41.pdf. 4a. Large test tube contains a liquid at room temperature. An electric heater is immersed in the liquid, and is switched on. Thermal energy is supplied to the liquid by the heater. The temperature of the liquid increases until it reaches its boiling point. The liquid then starts to change into gas. 8. Describe, in terms of molecules and their motion, how a liquid differs from a gas. Molecules closer. Molecules move only small distances between collisions or do not move freely. Molecules move in clusters or slide past each other. B. Describe what happens to molecules of the liquid as its temperature begins to increase. Molecules in liquid move faster or gain energy. Molecules move apart on average. C. I. Explain, in terms of molecules, why a supply of thermal energy is needed to change the liquid into a gas. Molecules overcome forces, gain potential energy as the liquid boils. E. The density of the liquid in the test tube is 0.86 grams per cc. The volume of liquid in the test tube is 50 cc. The liquid reaches its boiling point. It now absorbs 18,000 J of thermal energy and all of the liquid changes into a gas. Calculate the specific latent heat of vaporization of this liquid. Specific latent heat equals 3 m equals rho v in any form, or 0.86 times 50 or 43 grams. LV equals Q divided by m in any form, or 18,043 or 18,000 over 0.86 times 50. 420 J per gram, or 4.2 times 105 J per kilogram. 5A metal container is used to cook food. The metal container has thick walls. Hot cooking oil at a temperature of 120 degrees Celsius is poured into the container. 8. The outside surface of the container gets hot. Some thermal energy passes through the metal because vibrating atoms in the metal collide with neighboring atoms and transfer energy to them. Explain how the rest of the thermal energy is conducted through the metal container to the outside surface by another process. Electrons mentioned. Electrons travel a great distance through the metal, or vibrating atoms hit free electrons. Electrons hit distant particles or transfer energy to distant atoms. B. The outside surface of the container is brightly polished and shiny. Explain how this reduces the power that needs to be supplied to keep the oil at the correct temperature. Shiny surfaces are poor emitters of radiation. Infrared radiation mentioned. Less energy lost, or lost energy does not need to be supplied. C. The metal container is spherical. The spherical container has a smaller surface area than a long, thin container of the same volume. Explain the advantage of using a spherical container. Less thermal energy emitted. Less space for energy to be lost. 0625_W20_Ms_42.pdf. 3. The kinetic energy of air passing through a wind turbine every minute is 720,000 J. The electrical output of the turbine is 9.0 A at a potential difference P, D, of 240 V. Calculate the efficiency % of the wind turbine. Efficiency equals % 5. 3. Output. P equals V, or E equals VIT, or E equals PT in any form, words, symbols or numbers. Or P equals V, or P equals 240 times 9, or P equals 2160 W, or E equals 240 times 9 times 60 equals 129,600 J. Rate of energy input equals 720,000 60ths equals 12,000 J s. Or energy input equals 720,000 J. Efficiency equals 100 times output power, or 100 times output energy, input energy. Words, symbols or numbers. Efficiency equals 100 times 2,160 12,000ths. Efficiency equals 18%. 4. Fig. 4.1 shows a thermometer. The voltmeter reading is 5.4 millivolts. A. State the name of this type of thermometer. Thermocouple. B. Fig. 4.2 shows the same thermometer used to measure the temperature of liquid X. With the setup in Fig. 4.2, the voltmeter reading is 1.7 millivolts. Calculate the temperature of liquid X measured by the thermometer. Temperature equals 2. Delta T equals 1. 7/5.4 times 100. T equals 31 plus 20 equals 51 degrees Celsius. C. Suggest an application for which this type of thermometer is more suitable than a liquid and glass thermometer. Any application involving higher, lower temperatures or rapidly changing temperatures, or on vibrating machinery or remote sensing or data logging or small areas masses. 5a. Define specific latent heat. Thermal energy needed to change state. Of unit mass 1 kg of material not per degree Celsius. Explain the melting of a solid in terms of molecules and energy. Molecules must be separated or intermolecular bonds must be broken, overcome. Work done against bonds or energy is required, needed. Not increase of K, speed. B. An electrical heater is used to heat a liquid to its boiling point. Fig. 5.1 shows the apparatus. When the liquid is boiling, the heater supplies 1.26 megajoules of thermal energy. The mass reading, shown on the balance, decreases from 3,800 grams to 2,300 grams. Calculate the specific latent heat of vaporization of the liquid. Specific latent heat equals 3. E equals ml in any form, or L equals E divided by m words, symbols or numbers. M equals 1.5 or 1500 or 3.82.3. Or 3800. 2300. L equals 1.26. Times 106 divided by 1.5 equals 8.4 times 105 J per kilogram. C. State and explain a precaution to improve the accuracy of the value of specific latent heat. Calculated in B. Insulate or apply lagging insulation to container. Reduction of thermal energy, heat losses. 0625_W20_Ms_43.pdf. 5 Fig. 5.1 shows two metal plates A and B with a radiant heater placed midway between them. Metal plate A is shiny. Metal plate B is dull black. A piece of cork is attached to each plate using wax. The wax is a solid at room temperature and has a melting point of 37 degrees Celsius. A. State and explain what happens to the pieces of cork a few minutes after the heater is switched on. Cork on black plate, side B falls off before cork on shiny plate, side A. Black surface are better absorbers than shiny surfaces. Or shiny surfaces are better reflectors than black surfaces. Black surface are better absorbers than shiny surfaces. Or shiny surfaces are better reflectors than black surfaces and of infrared radiation. Wax on black plate, plate B melts before wax on shiny plate, plate A. B. Give the name of the method of transfer of thermal energy in solid metals. Conduction. 0625_W21_Ms_41.pdf. 2A student carries out an experiment using a plastic beaker that contains 0.24 kilograms of water at 17 degrees C. The thermal capacity, heat capacity, of the beaker is negligible. A. Define thermal capacity. Quantity of thermal energy or energy to increase temperature or energy transferred by heating. Energy to increase temperature of an object per degree Celsius 1 degree Celsius. B. Several ice cubes are at a temperature of 0 degrees Celsius. The ice cubes are dropped into the water and the internal energy of the water decreases. I. Give a simple molecular account of this decrease in internal energy. Internal energy depends on kinetic energy of molecules. Kinetic energy of molecules decreases or potential energy of molecules decreases. The specific heat capacity of water is 4,200 J kilogram degree C. Calculate the decrease in the internal energy of the water as its temperature decreases from 17 degrees Celsius to 0 degrees Celsius. Decrease in internal energy equals 2. Delta E equals mc delta T in any form, or 0.24 times 4,200 times 17. 1.7 times 104 J. C. As the temperature of the water decreases, some of the ice melts. I. Explain why this ice melts. K. E. Of molecules, thermal energy absorbed from water, surroundings, or energy absorbed from cooling water. Supplies latent heat or energy used to overcome intermolecular forces to break bonds. E. Describe how to determine the specific latent heat of fusion of ice using this experiment. State any other measurements that the student needs to make. Any determination of mass. Determine change in mass of ice, increase in mass of water, or dry the ice, or ensure water is at 0 degrees Celsius. Equilibrium is established or insulate the beaker. Use LF equals E per meter in any form. 3 Fig. 3.1 shows a balloon inflated with air. The pressure of the air at the inner surface of the balloon keeps the rubber stretched. A. Explain, in terms of the momentum of the molecules, why there is a pressure at the inner surface of the balloon. Any three of the molecules collide with inner surface. Momentum of a molecule changes, reverses. Force exerted, impulse. Force spread over area, surface or P equals F, A. B. The volume of the air in the balloon is 630 cc and the pressure of the air in the balloon is 1.0 times 105 pascals. The balloon is tied to a heavy stone and dropped into a lake. The balloon is pulled down quickly and the temperature of the air inside does not change. I calculate the volume of the air when the pressure of the air is 1.4 times 105 pascals. V2 equals P1 V1 P2 in any form or 630 times 1.0 times 105 over 1.4 times 105. 450 cc or 4.5 times 10 minus 4 centimeters 3 or 0.45 decimeters 3. E. The balloon and stone stop moving when the stone hits the bottom of the lake. The temperature of the air now begins to decrease. Explain why the volume of the air in the balloon decreases as the temperature decreases. Any two of molecules move more slowly, have less kinetic energy. Pressure inside balloon decreases or pressure is directly proportional to temperature or P proportional T. Volume is directly proportional to temperature or proportional T. Molecular collisions less frequent. Molecular collisions less violent, hard, exert smaller impulse. Water external pressure compresses balloon or water pressure greater and balloon compressed. 0625_W21_Ms_42.pdf 4a. A power station uses wind energy to generate electricity. State and explain whether this method of generating electricity is renewable. Statement: renewable. Explanation: wind is replaced, replenished or does not run out or is not used up or is an infinite energy resource. B. State two energy resources that do not have the sun as their source. Any two from geothermal, nuclear, tidal. C. For each energy resource, state the form of energy stored in fossil fuels, chemical, water behind hydroelectric dams, gravitational potential. 5a. A thermocouple thermometer is used to determine the temperature difference between a mixture of ice and water and liquid mercury at approximately 600 degrees Celsius. Complete Fig. 5.1 with a labeled diagram to show how the thermocouple thermometer can be used in this way. Wires of two different metals. One junction clearly in each liquid. Voltmeter, ammeter, galvanometer correctly connected. B. State two other physical properties that can be used to measure temperature. Any two from expansion of liquid, expansion of solid, expansion of gas, density of liquid, electrical resistance. C. State two benefits of using a thermocouple thermometer instead of a liquid in glass. Thermometer. Any two from large range, measure high temperatures, remote sensing, small size or small mass, small thermal capacity, suitable for data logging, responds quickly or measures rapidly varying temperatures or temperature changing continuously. 0625_W21_Ms_43.pdf 4. Explain what happens to the pressure of a constant volume of air when the temperature of the air increases. Use ideas of momentum of molecules in your explanation. Temperature of air increases so molecules move faster, their K increases. Molecules collide with walls of container and change momentum. Greater change of momentum when temperature is higher or collisions more frequent or harder collisions or force equals rate of change of momentum. Higher force and hence higher pressure. 5a. An aluminium saucepan and a steel saucepan have the same dimensions. Table 5.1 shows the values of the specific heat capacity and the density of aluminium and of steel. The mass of the aluminium saucepan is 0.41 kg. I calculate the mass of the steel saucepan. 1.2 kg, 7600 0.41 2600 m times equals volume constant so mass directly proportional to density. E. Calculate the thermal capacity of the aluminium saucepan. 0.37 J per degree Celsius. Thermal capacity equals mass times specific heat capacity. E. Water is heated in the steel saucepan. The initial temperature of the water in the saucepan is 20 degrees Celsius. Calculate the energy transfer needed to raise the temperature of the steel saucepan to 100 degrees Celsius. 48 J. E equals mc delta T or 1.2 times 0.50 times 100 to 20 in any form. B. Explain why metals are better thermal conductors than non-metals. Electrons mentioned. Metals have electrons free to move delocalized which transfer thermal energy. 0625_W22_Ms_4 extended 1.pdf. 4a quantity of gas is trapped by a piston in a cylinder with thin metal walls. The piston is free to move without friction within the cylinder. Fig. 4.1 shows the cylinder and piston. The cylinder is placed inside a freezer. The air in the freezer is at atmospheric pressure, which is 1.0 times 105 pascals. The area of the piston in contact with the air in the freezer is 2.4 times 10 to 3 m2. I calculate the force exerted on the piston by the air in the freezer. 240 N. F equals Pa in any form or 1.01052.4 10 to 3. E. When the cylinder is first placed into the freezer, the temperature of the gas in the cylinder decreases and the air pushes the piston into the cylinder. Calculate the work done on the piston by the air in the freezer as the air pushes the piston a distance of 0.021 meters into the cylinder. 5.0 J. WD equals Fx or 240.021. B. The initial temperature of the cylinder and the gas is 21 degrees Celsius and, in the freezer, the temperature of the cylinder decreases to -18 degrees Celsius. The thermal capacity of the cylinder is 89 J per degree Celsius. Calculate the change in the internal energy of the cylinder. -3.5103 J. E equals CdT in any form or 8921-18 or 89.3 or 89.39. C. When the temperature reaches -18 degrees Celsius, the pressure of the gas in the cylinder is still equal to that of the atmosphere. Explain, in terms of the particles of the gas, how the pressure remains equal to its original value. As the volume decreases, the particles collide more often. As the temperature decreases, the particles collide less violently. Two effects cancel to leave the pressure unchanged or particles collide with walls, piston, cylinder. D. As the temperature of the metal cylinder decreases, the volume of the metal decreases. The decrease in the volume of the metal is much less than the decrease in the volume of the gas. Explain, in terms of the particles of the metal, why the decrease in the volume of the metal is less than that of the gas. Attractive forces between any two particles larger than in gases. Particles closer together than gas particles or particles already touching. 0625_W22_Ms_4 extended 2.pdf. 4a. Explain, in terms of the momentum of particles, how a gas exerts a pressure. Any three from moving particles have momentum or particles hit walls. Momentum changes when particles hit walls. Force exerted by particles due to rate of change of momentum. Pressure is total force of particles per unit area of wall. B. The temperature of a sample of gas is increased at constant volume. State and explain any change in the pressure of the gas. Pressure increases. There is a greater change of momentum or particles exert greater force on same area or particles move faster or particles have more Ke. C. Another sample of gas is in a sealed container of volume 170 cc and exerts a pressure of 9.0 times 104 pascals. The volume of the container decreases by 70 cc at constant temperature. Calculate the new pressure of the gas. Pressure equals 1.5105 pascals. P1V1 equals P2V2 or P2 equals P1V1 V2 or PV equals constant for fixed M, fixed T. P2 equals 9.0104 and 170 100ths. 5 Fig. 5.1 shows an aluminium block after leaving a furnace in a factory. The mass of the block is 1200 kg and it is heated in the furnace from 20 degrees Celsius to 380 degrees Celsius. The aluminium block does not melt. The specific heat capacity of aluminium is 960 J kg C. Calculate the thermal energy gained by the block in the furnace. E equals 410 million J or 410 megajoules or 4.1108 J. E equals MCT or E equals MCT or 1200,960,360. T equals 360 degrees Celsius. B. Fig. 5.1 shows a factory worker standing 3 meters from the block. State and explain the main process by which thermal energy is transferred to the worker. Thermal radiation. Electromagnetic, EM, infrared, IR radiation emitted from block. Travels to worker or is absorbed by worker or travels without needing a medium. C. State and explain the main process by which thermal energy is transferred from the outer Surface of the solid metal rollers to their interior. Conduction. Delocalized, free, moving electrons. Any one from. Electrons move from outer surface to interior of rollers. Electrons travel throughout the solid, large distances. Electrons collide with distant particles. Lattice vibrations transfer thermal energy to neighboring particles, or particles vibrate and cause nearby, adjacent particles to vibrate, or vibrating particles collide with particles transferring energy. 0625_W22_Ms_4 extended 3.pdf. 3 Fig. 3.1 shows the cross-section of a barrage built across a tidal bay. The barrage is part of a tidal power station. The gates are raised to be open when the tide comes in. The gates are lowered to close when it is high tide. Fig. 3.1 shows the water levels in the open sea and the tidal bay when it is low tide. The gates are raised and water flows through the turbine. A. Complete the sentences to describe the energy transfers which take place when the gates are opened. Use words from the list. Tidal bay kinetic gates, gravitational potential. Open sea turbines, water. Gravitational potential energy of the water in the tidal bay is transferred to kinetic energy in the rotating turbines. This energy is used in the generator to produce electrical power. B. State one advantage and one disadvantage of tidal power as an energy resource. Any one advantage from. Renewable, reliable or predictable, running cost low, does not produce harmful pollution. Any one disadvantage from. High cost of construction, possible effects on marine life. Not available all day. Power produced doesn't always match with peak demand. Limited number of sites. Maintenance difficult, increased corrosion because underwater. C. State the main source of energy for tidal energy. Moon. 4a. Fig. 4.1 shows a liquid in glass thermometer labeled thermometer X. I. State the physical property which varies with temperature in a liquid in glass thermometer. Any one from. Volume of liquid. Length of thread, liquid in tube. E. Thermometer Y has a bulb that contains twice the volume of liquid compared to thermometer X. State and explain how the sensitivity of thermometer Y compares with the sensitivity of thermometer X. More or greater sensitivity. Volume of liquid, length of thread increases more per degree Celsius unit temperature because greater volume of liquid present. Or more liquid to expand, so gives a larger change in the level of the liquid per degree Celsius unit temperature. E. State and explain one change that can be made to the design of thermometer X2. Increase its range. Longer capillary tube. Liquid can expand further, so to a higher temperature. Smaller volume bulb. Less liquid, so liquid expands less, lower rise per degree Celsius. Larger diameter, wider capillary tube. Lower increase in level for each degree C. Replace liquid with a liquid with lower expansivity. Liquid expands less for each degree C. B. A liquid in glass thermometer cannot measure a temperature of 1300 degrees C. State a physical property which varies with temperature in a thermometer which can measure a temperature of 1300 degrees C. Electromotive force. 5a. 3 identical dishes, A, B and C, contain an equal volume of water. Dish A is outside in sunlight and experiences no wind during the day. Dish B is outside in sunlight and experiences a strong wind during the day. Dish C is in a dark room. Water evaporates from each dish. After 12 hours, a student measures the volume of water in each dish. Dish C contains the largest volume of water and dish B contains the smallest volume of water. Explain, in terms of particles, why the three dishes have different volumes of water. Energy from the sun transfers to, is absorbed by water molecules, so K of water molecules increases. Molecules with higher energy, K, faster moving molecules escape from the surface. Wind removes molecules when they have left the surface, so they do not re-enter the liquid. Any one from. Wind increases the rate of evaporation. Absorption of energy from the sun increases the rate of evaporation. Least, less water evaporates, lower rate of evaporation from dish C. Most, more water evaporates, higher rate of evaporation from dish B. B. Define specific latent heat of vaporization. Energy to change 1 kilogram unit mass from liquid to gas, gas to liquid without changing its temperature. Energy to change from liquid to gas, gas to liquid. Or energy to change state of 1 kilogram. C. Fig. 5.1 shows an insulating beaker, crushed ice, an immersion heater and a thermometer. The initial temperature of the ice is minus 60 degrees Celsius. The immersion heater is switched on and the temperature is recorded at equal intervals of time. Fig. 5.2 shows the temperature time graph. Describe what occurs in each of the sections A, B, C and D. A. Temperature of solid ice increases and C. Temperature of liquid water increases. B. Solid ice changes to liquid water or solid ice melts at constant temperature. D. Liquid water changes to gas, steam or liquid water boils at constant temperature. 0625_W23_Ms_41.pdf. 2A copper cooking pan contains water. Fig. 2.1 shows the pan on a hot plate of a cooker. A. Thermal energy is conducted through all solids by lattice vibrations. Describe one other way in which thermal energy is conducted through the copper. Ne3 from free, delocalized, mobile electrons. Electrons gain thermal energy from hot plate particles. Electrons move throughout copper, metal or electrons move to distant particles. Electrons transfer energy from higher temperature region to lower temperature region or electrons collide with distant particles transfer energy to distant particles. B. The outside surface of the cooking pan is kept clean by regular polishing. Explain one other advantage of keeping the surface of the pan shiny. Shiny surfaces are poor emitters of radiation. Reduces energy loss from the pan, copper or less energy transferred to surroundings. C. The thermal energy passes into the water through the base of the pan. Identify the main method by which thermal energy is transferred throughout the water. Convection. 5 Many methods of generating electrical power involve the use of water. A. Describe one method of generating electrical power from energy stored in water. Any. 3 From. Description of how the energy from water is released. Mention of transfers between energy stores. Moving water turns turbine. Turbine turns drives generator. Name of method to match description. B. For the method you chose in A, state one advantage and one disadvantage of generating electricity this way. Advantage of generating electricity from energy stored in water. Disadvantage of generating electricity from energy stored in water. C. State 2 methods of generating electrical power for which the main source of energy is not the sun. Any 2 from. Geothermal energy power. Tidal energy power. Nuclear energy power. 0625_W23_Ms_42.pdf. 2 Fig. 2.1 shows an electric tumble dryer used to dry wet clothes. A. Hot air blows into the drum. The air gains water vapor from the clothes and then leaves the drum. The moist air enters the condenser. Cool air leaves the condenser, passes through the heating element and enters the drum again. I. State the process by which the hot air removes water from the wet clothes. Evaporation. E. The air is cooled as it passes through the condenser. Describe and explain one other way in which the air leaving the condenser is different from the air entering the condenser. Air is drier, because water vapor has condensed, turned back to liquid in the condenser. B. The drum of the tumble dryer rotates, lifting up the wet clothes which then fall down through the hot air. I. Name the force that causes the clothes to fall down. Gravitational force or weight. E. When the drum rotates too fast, the clothes remain in contact with the wall of the drum. State the direction of the resultant force on the clothes during the circular motion. Force is perpendicular to the motion of the clothes. C. Suggest why using a clothesline to dry clothes in the open air is better for the environment than using an electric tumble dryer. Uses solar, wind energy which is renewable. Energy resources not used to generate electricity. Greenhouse gases not produced or does not use fossil fuels. 0625_W23_Ms_43.pdf. 4a. The lowest possible temperature is 0 Kelvin, 0 K. I. State the name of this lowest possible temperature. Absolute 0 or 0 K equals minus 273 degrees Celsius. E. Nitrogen boils at 77 K. Calculate the boiling point of nitrogen on the Celsius scale. Minus 196 degrees Celsius. B. The temperature of a fixed mass of gas at constant volume changes from 300 K to 400 K. State and explain, in terms of particles, the effect on the pressure of the gas. Increased pressure. Particles of gas move faster or have more K momentum velocity. Ne2 from. More frequent collisions of particles with walls. Particles collide with walls with a larger force or larger impulse. Greater change in momentum of particles causes greater force on walls. Pressure equals force area. C. A sample of gas is at a pressure of 120 kilopascals. The volume of the gas is doubled at constant temperature. Calculate the new pressure of the gas. Pressure equals 60 kilopascals or 6.0104 pascals. P1V1 equals P2V2 or P2 equals P1V1, V2 or PV equals constant. Or P1V or 1.21050.5 or 6.010 N.